session is Muhammad Thomas Vidade. He's going to talk about an axiomatization of constructive real numbers. Please start.
Thank you. Good afternoon, everyone. Many thanks to the organizers for organizing this workshop. I'm really happy to be here. I'm going to talk about an axiomatization of constructive real numbers. This is actually an ongoing work with Professor Muhammad Ardeshir and Dr. Mohsen Shahriari at Sharif University of Technology in Iran. In constructive mathematics, without the axiom of countable choice, there are at least 7 non-isomorphic definitions of real numbers. First of all, I'm going to present these 7 different definitions, and after that we try to axiomatize them. The first definition is the definition of fundamental sequences, which I denoted here by R to the F. Here every real number would be a fundamental sequence of rational numbers. We say that a sequence Rn of rational numbers with modulus alpha, which is a function from natural numbers to natural numbers, is a fundamental sequence of rational numbers if and only if it satisfies this condition. For all k, for all n, for all m, if n and m is greater than alpha k, the distance of Rn and Rm is less than 1 over k. It means that the terms of the sequence get closer and closer to each other. But this closing to each other has a bound, which is alpha. Therefore, if you want the distance to be less than 1 over k, you need to go after alpha k. You have a bound for the distance of the terms of the sequence. Okay, so here every real number is a fundamental sequence with modulus alpha. Now we need to define the equality relation between the elements. We can define an equivalence relation on R to the F. We say that 2 fundamental sequences Rn and Sn are equal or have a relation with each other if and only if this condition holds. This condition says that the terms of the 2 sequences get closer and closer to each other. In other words, they are approaching to the same point on the continuum. In that case, we consider them to be equal. Therefore, equality on R to the F is defined as this equivalence relation. Equality is not identity here. 2 fundamental sequences can be not identical, but can be equal. It's a very important distinction here. So, we define equality as this way. And one can define addition, multiplication, order, maximum, and minimum on R to the F with desired properties. The second kinds of real numbers is R prime to the F. I denoted it by R prime to the F. It is the set of all equivalence classes of fundamental sequences of rational numbers.
Sorry, may I ask a question? In the previous slide, you talked about the operation on RF.
Yes.
But for example, I mean, each real number is with the modulus alpha,
yes.
right? So,
Without.
For example, if you define the multiplication over RF, you need some, I mean, condition on translate the modulus
Yes.
pair of modulus to
Exactly.
other modulus, right?
Yeah. We need to define a new modulus of convergence for the
Yeah.
multiplication. Yeah.
In the case of multiplication, is it straightforward?
I think it's not very difficult to define the new modulus combining the alpha and beta. Given alpha and beta, we can define a new modulus of convergence for the multiplication of the two fundamental sequences. It's not very difficult to define.
Okay.
Yeah. In some sense, it's straightforward.
But you use modulus of convergence like 1 over n.
Yeah.
So if you use it's 1 over 2 to then it's
Yeah, it's more
easy.
Yeah.
Especially for calculating the
Yeah.
bound for multiplication.
Yeah, exactly. It's more easier. But it's not essential, but
Yeah,
it makes
not
it
essential.
easier, yeah.
Okay. Okay, thank you.
Okay, all right. For defining r prime to the f, you just need to take quotient by that equivalence relation. If you divide r to the f by that equivalence relation, you get r prime to the f. Therefore, here every real number would be an equivalence class of fundamental sequences, not an individual fundamental sequence. In other words, if I want to explain more, let x be a fundamental sequence of rational numbers. The class of x is the set of all y's such that x approx y. Therefore,
Can I see the definition of approx?
yes,
Sorry.
the definition of approx is this.
Okay, system. Okay, thank you.
You're welcome. Therefore, every real number is a set, actually. It's not sequence. Now we can define equality on r prime to the f as identity of sets. Here, equality is exactly identity. This is an advantage of the definition of r prime to the f. You can simply define equality as identity of sets. One can define addition, multiplication, order, maximum, and minimum on r prime to the f with desired properties. Therefore, here every real number would be an equivalence class of fundamental sequence.
Do you work over intuitionistic logic constructively?
Yes, constructive mathematics without assuming the axiom of countable choice.
Really?
Yeah. Yeah.
Okay. It's possible. Okay.
So there's no so the modulus alpha is no use in that in the second definition.
Actually, the whole fundamental sequences which are in relation with this fundamental sequence is inside this equivalence class. The third definition is the Cauchy sequences of rational numbers. Here, every real number would be a Cauchy sequence of rational numbers without modulus of convergence. Therefore, we say that Rn, which is a sequence of rational numbers, is a Cauchy sequence of rational numbers whenever this condition holds. This condition again says that the terms of the sequence get closer and closer to each other, but there is no bound for that. For every k, there exists a number n, such that after that, the distance is less than 1 over k. Okay? Therefore, here every real number would be a simple sequence of rational numbers without modulus of convergence. We can define an equivalence relation on r to the c with exactly the same way as before. And we can define equality on R to the C as before. Therefore, for R to the C, again, the equality is not identity. It's an equivalence relation. One can define addition, multiplication, order, maximum, and minimum on R to the C with desired properties. And again, we can take quotient again, and we can construct R prime to the C, which is the set of all equivalence classes of Cauchy sequences of rational numbers. If I want to explain more, let X be a Cauchy sequence. The class of X is all Y such that Y approx X. Therefore, every real number here would be a set, would be a class of, equivalence class of Cauchy sequences. We can define equality on R prime to the C as identity of sets. Therefore, here every real number would be an equivalence class of R to the n. Again, one can define addition, multiplication, order, and maximum and minimum with desired properties. Okay, these 4 definitions are discussed in a paper of Robert Lobarsky, and he actually separates these 4 definitions of real numbers. Therefore, in constructive mathematics, without assuming axiom of countable choice, we cannot prove that these 4 definitions are isomorphic. We cannot prove the existence of isomorphism. All of these constructions are constructed with Cauchy method. Now I'm going to present the Dedekind method. There is also, again, 3 different versions of real numbers here. I'm introducing them simultaneously. Okay, let L be a subset of rational numbers. L is called a weak left cut or bounded extended real if it satisfies 3 conditions, A, B, and C. Let me draw a picture here. Suppose that this is a real line. This is supposed to be L. The first condition is inhabitedness. Inhabitedness says that there exists a rational number R such that R is inside L. And there exists another rational number S such that S is outside L, is not in L. So there exist 2 rational numbers with these properties. The second property, the second condition says that if it's called downward closeness. It says that if R is in L and there exists another rational number S such that S is less than R, we can be sure that S again is in L. It's downward closed. And the other condition is called openness, which says that if we know that R is in L, then there exists another rational number R prime, which is greater than R and still is in L. Therefore, it's open. It's not closed. Okay. The set of all bounded extended real numbers is called R to the BE by Troelstra and Van Dam. R to the BE, bounded extended reals. If you replace A with A prime, you get another kind of real numbers. A prime says that this L is non-empty. Therefore, you just need to replace inhabitedness with non-emptiness. We know that non-emptiness and inhabitedness are not equivalent in constructive mathematics. Therefore, if you replace inhabitedness with non-emptiness, you get extended real numbers or classical real numbers, which is denoted by R to the E. And if L satisfies D besides A, B, and C, it's called a Dedekind cut or a Dedekind real. The condition D is called locatedness, which says that if we know that R is less than S, we can decide whether R is in L or S is not in L. Therefore, the set of all Dedekind reals is called R to the D. It's denoted by R to the D. We can simply see that R to the D is a subset of R to the BE, and it's a subset of R to the E. And Troelstra and Van Dalen show that these three definitions are actually separate. We cannot prove that they are equivalent to each other in constructive mathematics without countable choice. So here we have 7 non-isomorphic definitions of real numbers.
Sorry, I'm a little bit confused. You said L is extended to real if the A conditions ABC holds, and you said the L is.
Let me say it again.
Okay.
R to the BE satisfies 3 first conditions, A, B, and C. If you replace A with A prime, you get R to the E.
That is extended to real.
Yes, that is extended reals. Or classical reals or weakly bounded cuts, there are a lot of names.
Okay.
And if L satisfies all 4 A, B, C, and D, then it's Dedekind.
Okay.
Yeah.
Okay. I see. Thank you.
Okay. Now we try to present some axioms such that all the 7 different definitions of real numbers serve as models. In other words, all of them satisfy these axioms. We need some definitions and lemmas here. Let A and B be sets and approx 1 and approx 2 be equivalence relations on A and B, respectively. Let F be a subset of A times B. Be a relation which assigns to any A in A an element in B. In other words, the domain of F is A. In other words, F is total, a total relation. We say that F is a pseudo function whenever F is a function up to the equivalence relations. In other words, for all x and y in A with x approx 1 y, we have f of x approx 2 f of y. We say that this pseudo function is 1-to-1 whenever it is 1-to-1 up to the equivalence relations. In other words, for all x and y in A with f of x approx 2 f of y, 1/2 x approx 1 y. Obviously, identity is an equivalence relation on every set. Therefore, if x approx 1 and approx 2 are identity, then f is a function if and only if it is a pseudo function. Therefore, the notion of pseudo function is just a generalization of the notion of function. And it's 1-to-1 if and only if it is 1-to-1 pseudo function. Let A be a set and n be a natural number. By A to the n, we mean the set of all n tuples of the elements of A. Let A be a set and approx be an equivalence relation on A and n be a natural number. Consider 2 elements of A to the n. We say that these 2 elements are equal to each other with respect to that equivalence relation whenever for each I, AI approx BI. One can easily check that this approx is an equivalence relation on a to the n. Therefore, if a is given with an equivalence relation, a to the n is again as an equivalence relation. Let a be a set, approx be an equivalence relation on a, and n be a natural number. We say that p, which is a subset of a to the n, is a pseudo relation on a to the n whenever this condition holds. For all two elements of a to the n, if one element is in p, and these two elements are in relation with each other, then the other element is also in p. In other words, this p respects the equivalence relation. From now on, when a0, a1, and an is in p, we simply write p of a0, a1, and a. If approx is identity, then p is a relation, if and only if it is a pseudo relation. Therefore, the notion of pseudo relation is just a generalization of the notion of relation. We say that R approx, C0, C1, and so on, F0, F1, and so on, P0, P1, and so on, is a pseudo structure. Whenever R is a set, approx is an equivalence relation on R. Each Ci is a fixed element of R. Each Fi is a pseudo function from R to the n to R for some natural number n, and each Pi is a pseudo relation on R to the n for some natural number n. This is the notion of pseudo structure. Therefore, you just need to see that as a structure, you just need to replace the identity relation with an equivalence relation, which I denoted it here by the symbol approx. Okay. Now let R approx 0, 1, addition, multiplication, in order, be a pseudo structure. We say that it is a pseudo partially ordered ring, or simply pseudo ordered ring, whenever it satisfies the universal closure of the following axioms. These axioms are exactly the axiom of partially ordered ring. You just need to replace the equality, the identity relation with the equivalence relation. For example, consider the axiom 1. X plus y is not necessarily identical to y plus x, but they are in relation with each other. X plus y approx y plus x. And these four first conditions are the axioms for addition, and after that we see the axioms for multiplication, and the axioms of order, and the axioms which relate order and addition, order and multiplication. The axiom element is very important here. It relates the order with approx. If we know that x is not less than y and y is not less than x, we can say that x approx y and vice versa. This is exactly the axiom, one of the axiom of partially ordered ring, if you replace approx with identity. If approx is identity, then this structure is an ordered ring if and only if it is a pseudo-ordered ring. Therefore, pseudo-ordered ring is just a generalization of ordered ring. Now let two structures, let R and R prime be two pseudo structures. We say that the pseudo function phi from R to R prime is a pseudomorphism whenever the following hold. These conditions are exactly the conditions of homomorphism between the structures. You just need to replace the identity with the relation approx. For example, phi fixes every fixed element Ci's, and respects functions and respects relations up to the equivalence relation. We say that this pseudomorphism is pseudo-isomorphism whenever it is one-to-one and onto. One-to-one up to the equivalence relations. In that case, we say that these two structures are pseudo-isomorphic. Again, if the proxies are identity, the notion of homomorphism and pseudomorphism coincides. And the notion of isomorphism and pseudo-isomorphism coincides. And the notion of pseudo-isomorphic and isomorphic coincides. Now let R and R prime be two pseudo-structures. We say that R prime is a substructure of R whenever the following is true. This is exactly the definition of substructure. We just need to replace the notion of identity with equivalence relation. For example, the structure of integers is substructure of the structure of rational numbers, because the structure of rational numbers doesn't destroy anything. It's just an extension of the structure of integers. This is an example here. It makes the notions very clear. The set of the individual rational numbers, which we denoted by Q, is the set of all fractions m over n, such that m is an integer and n is a natural number which is non-zero. The relation approx is defined on Q as follows. For all fractions a over b and c over d, a over b approx c over d if and only if a times d equals b times c. This is not the identity relation, this is an equivalence relation between fractions. We can define addition, multiplication, order, maximum, and minimum on Q as this for all fractions a over b and c over d. Addition is defined as usual, explicitly, and also multiplication and also order. Everything is defined explicitly, and also maximum and minimum. Everything is clear. It can be easily checked that approx is an equivalence relation which respects all of operations and relations. For example, if two fractions are in the relation approx, then the additions also is in relation approx. And the most important axiom which is satisfied here is the axiom 11. For all a over b and c over d, if a over b approx c over d, we can conclude that a over b is not less than c over d, and c over d is not less than a over b, and vice versa. It can be easily checked that the structure Q approx 0, 1, addition, multiplication, and order, where 0 is the individual rational number 0 over 1, and 1 is the individual rational number 1 over 1, is a pseudo-ordered ring. It's not an ordered ring because the equality is not identity, it's an equivalence relation. The set of rational numbers which is denoted by Q prime is the set Q divided by the equivalence relation. You just need to take quotient. That is the set of all inhabited equivalence classes of individual rational numbers. Because for every fraction c over d, we can find, for every fraction a over b, we can find another fraction c over d such that GCD of c and d is 1, and a over b approx c over d. Every rational number class of a over b has a unique representative. We don't need the axiom of countable choice to select a representative from every equivalence class. We can define addition, multiplication, and order and maximum and minimum as before. You just need to work with equivalence classes instead of individual rational numbers. And you can see that the structure Q prime, identity, 0, 1, addition, multiplication, and order is a pseudo-ordered ring, and 0 is the class of all fractions which is the class of all fractions which is in the relation with 0 and 1, 0 over 1, and 1 is the same. It's pseudo-ordered ring. Since the equivalence relation is identity, it is an ordered ring. It's not only a pseudo-ordered ring, but it's ordered ring. Now I'm going to define the notion of Q extending ring, which is very important notion for further discussion. We say that a pseudo structure R, approx 0, 1, addition, multiplication, maximum, minimum, and order is a Q extending ring whenever the following holds. First of all, the structure R approx 0, 1 time addition, multiplication, and order is a pseudo-ordered ring. Therefore, it satisfies all those 13 conditions. The axiom 2 and axiom 3 are the axioms for maximum. For example, maximum of x and y is less than t implies x is less than t and y is less than t. And if t is less than maximum of y and x and y, implies t is less than x or t is less than y. And the axioms for minimum are just dual of the axioms for maximum. And 6 says that the structure of rational numbers is a pseudo-isomorphic to a substructure of this structure. Therefore, every Q extending ring it's an extension of the structure of rational numbers. And the axiom 7 says that Q must be weakly dense in R. That is for all two elements in R, x and y, such that x is less than y. We can conclude that it's not the case that there is no rational number Q such that Q lies between x and y. It's definitely weaker than density because it doesn't say that there exists a Q. It says that it's not the case that there is no Q such that. And the axiom 8 says the triangle inequality holds. Obviously, Q itself is a Q extending ring. And let R be a Q extending ring. By definition, Q is a pseudo-isomorphically a substructure of R. So it's not always true that Q is literally a subset of R. But by abuse of notation, as it appeared in the axiom 7 here, we can assume that Q is a subset of R. This assumption is harmless, but makes it easier to write and read. We can define non-strict order on Q extending rings, as usual, the negation of order. Now we have a good theorem here. All of these 7 structures of real numbers are Q extending rings, satisfy all the axioms I just presented. So we have made good progress so far. We found some good axioms such that all of these 7 satisfy them, but we have not completed yet because Q is also a Q extending ring. We need to distinguish the structure of rational numbers. We need to exclude the structure of rational numbers from the other definitions of real numbers. But what makes rational numbers different from real numbers? It's just completeness property. So we have to define some sort of completeness property such that all of the 7 definitions satisfy that completeness property. Okay, let R be a Q extending ring. A sequence xn in R is convergent whenever there exists x in R such that the sequence converges to that x. This is just simply the definition of convergence. In that case, we just write limit of xn is x. We can prove that if a sequence is convergent, the limit point is unique up to the equivalence relation. Now we can define the notion of Cauchy sequence. Let xn be a sequence in R. Please note that every element of this sequence is an element of R. We say that it is a Cauchy sequence whenever the terms get closer and closer to each other, the usual Cauchy condition. Let R be a Q extending ring. Every convergent sequence in R is a Cauchy sequence. We can prove that easily. But the converse is not always true. It's not the case that every Cauchy sequence in a Q extending ring is a convergent sequence. For example, consider Q itself. We can construct a Cauchy sequence in Q which is not convergent to any rational number. Therefore, we have a motivation to define a sort of completeness property. A Q extending ring R is Cauchy complete whenever every Cauchy sequence in R is convergent. By Troelstra and Van Dalen together with Bridges, we can conclude that these three definitions, R to the D, R to the BE, and R to the E, are Cauchy complete. Therefore, these three definitions are Cauchy complete. Now let R be a Q extending ring. A sequence xn in R is modulated Cauchy sequence whenever there exists a function alpha such that this condition holds. This is exactly the Cauchy condition, but with respect to the modulus of convergence alpha. We have a bound for the convergence. It's not the case that every modulated Cauchy sequence is convergent. For example, consider Q itself. We can construct a modulated Cauchy sequence in Q which is not convergent to any rational number. Therefore, we have a motivation to define another sort of completeness property. A Q extending ring R is weakly Cauchy complete whenever every modulated Cauchy sequence in R is convergent. It's simply a weaker notion of completeness, because if every Cauchy sequence is convergent, we can be sure that every modulated Cauchy sequence is convergent. For example, R to the F and R to the C, according to Lewarsky, are weakly Cauchy complete. Every Q extending ring which is Cauchy complete is weakly Cauchy complete, obviously. But the other direction is not true. There exist Q extending rings which are weakly Cauchy complete but cannot be constructively proved to be Cauchy complete. For example, R to the F and R to the C. They are weakly Cauchy complete, but it cannot be constructively proved to be Cauchy complete by Lewarsky. Now, what about R prime to the F and R prime to the C? The set of all equivalence classes of Cauchy sequences. According to Lewarsky, it cannot be constructively proved that R is weakly Cauchy complete. Therefore, R prime to the C and R prime to the F is not weakly Cauchy complete and is not Cauchy complete. Therefore, the question is, what sort of completeness property do they have? Because they must have some sort of completeness property. There is a theorem. Every definitions of real numbers here, R to the C, R to the F, R to the D, R to the B, R to the E, are weakly Cauchy complete. Let me summarize these results. That all of these 7 structures are Q extending rings. All of them are Q extending rings. R to the D, R to the B, R to the E are Cauchy complete. Therefore, they are also weakly Cauchy complete. R to the F, R to the C are weakly Cauchy complete, but cannot be constructively proved that they are Cauchy complete. R prime to the F and R prime to the C, it cannot be constructively proved that they are Cauchy complete, and also it cannot be constructively proved that they are weakly Cauchy complete.
I have a question. You define the weakly Cauchy complete by using additional assumption
Yes.
on modulus,
Yes.
information modulus.
Exactly.
So, how do you consider the notion of modulus for Dedekind trials or
Exactly the same as before. For example, let me Cauchy sequence. Here. Let R be a Q extending ring.
Mhm.
A sequence xn in R is modulated Cauchy sequence whenever there exists a function alpha from natural numbers to natural numbers such that this condition. This doesn't depend on
Okay.
any kind of structure of
Okay. It's just a function
Yes.
from
Exactly.
Okay. Sorry.
Yes. Thank you. Okay. So R to the D, R to the B, R to the E have some sort of completeness property. Also R to the F and R to the C, but R prime to the F and R prime to the C doesn't have any. Doesn't see, so far we don't have any kind of completeness property they satisfy. Now we can define real number system here eventually. We say that the structure R approx 0, 1, addition, multiplication, maximum, minimum, and order is a real number system whenever the following is hold. First, it is a Q extending ring. Therefore, it must satisfy all that exists. Second, there exists a weakly Cauchy complete Q extending ring S prime. There exists a weakly Cauchy complete Q extending ring S and an onto pseudomorphism phi from S to R such that it fixes the rational numbers. And we can see that all these 7 structures of real numbers are real number systems.
Sorry, could you?
Yes, I'm going to explain this definition.
Type is correct because phi is a morphism from S to R.
Yes?
But you write for all R in Q.
Q, yes. Because both S and R are Q extending rings.
Okay.
Both of them are Q extending rings.
So Q is a subset of
Exactly.
S.
Q is a substructure of S and also a substructure of R.
Oh, okay. I see.
Yeah. And phi must fixes the rational numbers.
Okay. I see.
Okay. For example, R to the F is weakly Cauchy complete. It's a Q extending ring, therefore it satisfies the first condition. It's a Q extending ring. And it's also itself a weakly Cauchy complete Q extending ring. Therefore, we can just consider the identity function from R to the F to R to the F. Therefore, it satisfies this definition. R to the F is a real number system. And all R to the C, R to the D, R to the B, R to the, all of them are weakly Cauchy complete themselves. Therefore, we just need to consider the identity function. But what about R prime to the F? R prime to the F is not weakly Cauchy complete constructively. We cannot prove that. But it's a homomorphic image of R to the F, which is weakly Cauchy complete. You just need to send every fundamental sequence of rational numbers to its equivalence class. With modulus R. And this, we can prove that this is actually, easily prove that this is actually a pseudomorphism, which is onto. Therefore, it satisfies the second condition. We can also do the same for R prime to the C. Therefore, all these 7 structures are real number system, but Q itself is not a real number system because it doesn't satisfy conditions. We excluded rational numbers. Okay, all of them are real number systems. Now the axiomatization is over. We have done that. Now we present some theorems concerning real number system. The first and very interesting theorem is that the real number system R to the F is the smallest real number system. In other words, for every real number system R, there exists a unique one-to-one pseudomorphism G from R to the F to R, such that G fixes rational numbers. In other words, every real number system has a copy of R to the F as a substructure. We can embed R to the F into every real number system. Now, we are going to investigate the notion of decomposability. Let X be a set. We say that X is decomposable whenever there exist 2 inhabited disjoint subsets of X, namely A and B, such that X equals A union B. For example, the real numbers R in classical mathematics is obviously decomposable because R can be written as Q union QC by the law of excluded middle, or the singleton 0 and the all real numbers which are non-zero. But we have a theorem here. Let R be a real number system. The decomposability of R implies the sequential version of WLPO, which uniformly implies that none of these structures of real numbers are decomposable constructively, because the decomposability of them implies WLPO. We proved that for arbitrary real number system. Therefore, it holds for all of them. And we could prove that if R is a real number system, the decomposability of R is actually equivalent to an analytic version of WLPO for R. Analytic version of WLPO says that for all X in R, either X approx 0 or not X approx 0.
So in the previous slide, you mentioned about the sequential version
Yes,
of RPO. Does that mean just for all sequence Rn of R?
No, it says that for all binary sequence, for every binary sequence, either all terms are 0, or it's not the case that all terms are 0.
Okay.
The same WLPO in the literature, sequential WLPO. Weak limited principle of only signs. For all binary sequence, either all terms are 0, or it's not the case that all terms are 0.
Sorry, could you say again? So
let me write it here. For all binary sequence alpha,
okay.
either for all n alpha n is 0, or it's not the case that for all n alpha n is 0.
Okay. So why you call that a sequential version?
Because it's concerning binary sequences.
Oh, okay.
Yeah.
For me, it's also analytic version.
Yeah. It's an analytic version because it concerns the real numbers.
Okay,
yes.
okay. I see what your intention. Okay.
Yeah. Okay. The decomposability of R is actually equivalent to the analytic version of WLPO. If you decompose R in any way, by any two subsets, then you can also decompose it by these two sets, singleton 0 and all real numbers which are non-zero. This is the theorem actually. Okay, let R be a real number system. The decomposability of R minus 0 implies the sequential version of disjunctive version of Markov's principle. This is just that sequential version which is appeared in the literature of constructive reverse mathematics. And the decomposability of R minus 0 is actually equivalent to the analytic version of disjunctive version of Markov's principle, which is this statement for all x in R minus 0, either x is less than or equal to 0, or x is greater than or equal to 0. This is the analytic version of disjunctive version of Markov's principle. Therefore, it holds for all of them uniformly, because we proved this theorem for an arbitrary real number system. Now, let R be a real number system. The decomposability of R minus Q implies again sequential version of disjunctive version of Markov's principle. Therefore, it's not constructively provable, because sequential version of Markov's principle is not. And the decomposability of R minus Q is actually equivalent to this statement for all non-rational real number, either it's less than or equal to 0 or greater than or equal to 0. Now there is an open problem here. Is the decomposability of R minus 0 is equivalent to the decomposability of R minus Q? Because, for example, in R to the F, if R is R to the F, these two are actually equivalent. Both of them are equivalent to sequential version of Markov's principle. But what about arbitrary real number system? In other words, do these two statements are equivalent or not? This is an open problem here. Okay, these are references, Bridges, Lobarsky, and Troelstra and Van Dalen. And that's it. Thank you.
Any question or comment?
That analytic version always implies the sequential version. Is correct?
Yes.
But converse is
Yes.
not the case.
The converse is not the case in some of them. For example, for R to the F, the converse is again true.
Oh, really?
Yes.
Well, in some cases,
It's true.
converse is also.
Yes. But for some cases, for example, R to the D, or Dedekind constructions, Dedekind reals, it cannot be proved.
Oh, it's interesting. Okay.
Yeah.
So, what's the difficulty from the compass in Dedekind theorem?
The converse cannot be constructively proved for Dedekind reals,
Yeah.
because if we don't have the axiom of countable choice, we cannot extract the sequence
Okay.
in a similar way.
Okay.
In the presence of countable choice,
Yeah.
the converse is also the case.
Yes. For R to the
Really?
D, yes, it's the case.
For any of.
I'm not sure for any of them, but I'm sure for R to the D it's okay. But for R to the B and R to the E, I'm not sure. Maybe it's not okay even there. Because Troelstra and Van Dalen have proved that the isomorphism, the existence of isomorphism between R to the D and R to the BE is actually equivalent to WLEM, weak law of excluded middle. Maybe we need more than countable choice.
You mean need some classical logic?
Yeah, we need some classical WLEM. The equivalence between R to the D, the isomorphism between these two, is requires WLEM.
Okay.
Actually equivalent. Therefore, I'm not sure that also in R to the B it's the case. But I'm sure that for R to the D, if we assume countable choice, then R to the D is actually equivalent to R to the F, isomorphic to R to the F. Therefore, the sequential version and analytic version are equivalent.
Okay, yeah.